Hello, and welcome to my video series on algorithms. This is part 3 of Module 6, Dynamic Programming. In this video, we'll be discussing the knapsack problem. Imagine you are preparing for a hike and need to pack your backpack. The backpack can only hold a certain maximum weight. You have a candidate set of items to choose from, each with its own weight and value. Some items, like water, are heavy and valuable, while the other ones, like sandwich, are lighter but still useful. Your task is to decide which items to bring, such that their total weight stays within the limit of the backpack, while maximizing the total value of the items you pack. Formally, let C be the maximum weight the backpack can hold, also known as the capacity, and let I represent the set of candidate items to choose from. Each item I in this set has a weight of Wi and a value of Vi. The goal is to find a subset of items, denoted as I', such that the total weight of the items in I' is less than or equal to the capacity C, and the total value of these items is maximized. First, let's consider whether this problem can be solved using greedy algorithms. Take the following example. We have a backpack with a capacity of 6 units and can choose from the 4 listed items. For instance, a drink weighs 4 units and adds a value of 9 to your trip. From this, we can calculate the per unit value of drink as 9 divided by 4, which equals 2.25. Based on this, we can propose 3 greedy strategies. We could select the most valuable item first, the lightest item first, or the item with the highest per unit value first. Let's first try the strategy of selecting the most valuable item first. In the selection column of the table, we will label the order in which the items are considered based on the corresponding greedy criterion. The drink has a value of 9, making it the most valuable item, so it will be considered first. Starting with a total capacity of 6, selecting the drink requires 4 units of capacity, which is available. Therefore, we place the drink into the backpack, leaving a remaining capacity of 2. Next, we'll consider switch and the sandwich, ranked second and third in terms of value. However, both require 3 units of capacity. Since only 2 units of capacity remain, neither switch nor the sandwich can be selected. Finally, we consider the last item, the stuffy toy, which requires only 2 units of capacity and still fits into the backpack. Thus, we select the stuffy toy. In total, we have selected drink and stuffy. Their combined weight is 6, which is within the capacity limit. Their total value is 10, but it is not optimal, as selecting switch and the sandwich will yield a total value of 11. Therefore, the greedy criterion of choosing the most valuable item first does not yield an optimal solution. The second greedy strategy we will try is selecting the lightest item first. Item 4, the stuffy toy, has the lightest weight of 2 units. So, we select it, leaving a remaining capacity of 4. The next lightest item is switch, which requires 3 units of capacity and can still be fit into the backpack. By following this strategy, we select the stuffy toy and switch, resulting in a total value of 7. However, this total value is not optimal either. Finally, we test the strategy of selecting the item with the highest per unit value first. In this case, we select drink and the sandwich, which have a combined value of 10. The selection is again not optimal. As a result, none of the greedy strategies work for this instance. Next, we'll attempt to solve this problem using dynamic programming. Let's begin with defining the subproblems. First, know that the maximum value we can achieve depends on two factors: the total capacity of the backpack and the set of candidate items we can choose from. Therefore, we define VCI as the maximum value that can be obtained with a maximum capacity C and the candidate item set I. For a smaller capacity C' and a subset of items I', we can define a corresponding subproblem VC', I'. Know that, unlike the weighted interval scheduling problem, which is defined using a single parameter, the knapsack problem is defined by two parameters. In fact, there is no restriction on the number of parameters you can use to define a subproblem. You can use as many as needed. With the subproblem definition, we now need to check whether the problem can be solved using dynamic programming. In other words, we need to verify two key properties: the overlapping subproblems and the optimal substructure. To verify these two properties, let's first discuss how to solve a larger problem using solutions of smaller subproblems. Suppose we have found the optimal solution for capacity C' and candidate item set I', represented by the yellow bars in the figure. A straightforward way to extend the current item selection to a larger scale is to add a new item to the backpack. Let the new item be I. To accommodate item I, we need to increase the capacity from C' to C' plus Wi. At the same time, the candidate set must include small I, becoming I' union small I. As a result, the maximum value under this configuration is denoted as V C' plus Wi, I' union small I. Since the value is achieved by adding the new item I, the new value is calculated by adding Vi to the previous maximum value V C' I'. In other words, we have the relationship V C' plus Wi, I' union small I equals V C' I' plus Vi. This is one possible way to solve a larger problem from the solution of a smaller subproblem. With this intuition, we can proceed to verify the overlapping subproblem property. In the previous example, we assume that the newly added item is I. In that case, we have V C' plus Wi, I' union small I equals V C' I' plus Vi. Following the same logic, if we assume the added item is J, we have V C' plus Wj, I' union small j equals V C' I' plus Vj. And if the added item is K, we'll have V C' plus Wk, I' union small k equals V C' I' plus Vk. We can observe that the term V C' I' is common across the right-hand sides of all three equations. It indicates that the solution to the problem V C' I' can be used to construct solutions to multiple larger problems. Therefore, our subproblem definition does satisfy the overlapping subproblem property. Next, we will verify the optimal substructure property. Consider the equation V C' plus Wi, I' union small I equals V C' I' plus Vi. Since Vi, the value of item I, is a constant, the maximum value of V C' plus Wi, I' union small I can be achieved when V C' I' is maximized. Therefore, The optimal solution to the larger problem relies on the optimal solution of the smaller subproblem. This confirms that our subproblem definition does have the optimal substructure property. After confirming that the problem can be solved using dynamic programming, we can proceed to design the algorithm. We will follow the three main steps for designing DP algorithms. Establish the partial ordering of the subproblems, write top-down recursion, and perform bottom-up tabulation. First, let's establish the partial ordering of subproblems. Recall the figure that illustrates how to solve a larger problem using solutions to smaller subproblems. In that example, we add a new item to the existing collection and adjust the capacity and candidate set accordingly. We observe that subproblems defined with larger capacities and candidate item sets correspond to larger subproblems and depend on those with smaller capacities and candidate item sets. However, to precisely define the dependency, we also need to consider constraints on the candidate set compositions and capacities. We will discuss each of these constraints next. Let's first discuss the constraint on the composition of the candidate sets. The composition is crucial because the solution of a larger problem is constructed by adding a new item to the existing collection. This means that the candidate sets of two dependent subproblems should differ by exactly one item. For example, the subproblem Vij cannot be used to solve VPQR because their candidate sets differ by more than one item. In such cases, we cannot easily compute the new value by swapping multiple items at once. To ensure proper subproblem dependency, the easiest way is to consider subproblems by adding items one at a time. For instance, if we start with a candidate set I, we then consider candidate set ij, which has exactly one more item. We then consider ijk, then ijkl, and so on. This way, we can ensure that the previous subproblem considered is needed by the next subproblem, as their candidate sets differ by exactly one item. If we adopt this approach, we will need to specify in which order we should add the items. Remember that a subproblem is defined with the candidate item set, which is unordered by definition. Therefore, the order in which we add items does not matter. For example, the two subproblems VC' ijk and VC' kji should have the same optimal solution, because we are selecting from the same set of candidate items. In other words, we can add the items in any order, and it won't affect the optimality of the solution. Next, let's look at the constraint on the capacity. We know that one way to construct a larger problem is to add a new item, say K, into the backpack. In this case, the backpack requires an additional WK units of capacity to hold the item. It implies that the capacity difference between two dependent subproblems should be WK, where K is the item that differentiates the two corresponding candidate sets. Another scenario to consider is leaving the item K out of our selection. In this case, no new item is added, and the capacity requirement remains the same. This implies that the capacity difference between two dependent subproblems can also be zero. Therefore, the capacity difference between two dependent subproblems should either be WK when adding item K, or 0 when not adding item K. Combining the constraints on both the candidate set composition and the capacity, we define the following partial ordering. given two subproblems VC1I1 and VC2I2. VC2I2 depends on VC1I1 if both of the following conditions are met. First, I2 equals I1 union K, meaning that I2 is formed by adding one item to I1. Second, C2 equals C1 plus WK, or C2 equals C1, meaning that the capacity increases by the weight of item K or remains the same. Now, let's proceed to the second step and write the top-down recursion. As discussed before, we have two choices for item K, to select it or not. If it is not selected, the capacity and value remain unchanged. The only change is that item K should be removed from the candidate set, because it has now been considered. This scenario corresponds to the first condition of the recursive function. On the other hand, if item K is selected, we need to update both the capacity and the value accordingly. Item K also needs to be removed from the candidate set, for that it has now been considered. This scenario corresponds to the second condition of the recursive function. With the recursion function defined, we will now design the bottom-up tabulation process. First, note that each subproblem is defined by two parameters, the capacity and the candidate set. As a result, we need to use a two-dimensional matrix, say M, to store the results of the subproblems, with one dimension for each parameter. Specifically, the entry Mij will store the result Vi 1 through j, which represents the optimal solution with a maximum capacity of I and a candidate item set containing the first j items. Let's again consider the instance we showed at the beginning of this video. The total capacity of the backpack is 6, and there are 4 items to choose from. In this case, we should allocate a 6x4 matrix as the DP table to store the results of the subproblems, with 6 representing the capacity and 4 representing the number of items. According to the recursion function, we know that the subproblem Vi 1 through j depends on its left subproblem Vi 1 through j minus 1 and its top left subproblem Vi minus wj 1 through j minus 1. It is important to know that the number of rows we look back is wj, which varies based on the item corresponding to the current column. With the dependency relationship, we set the table filling order as left to right and row by row. This approach ensures that all dependent subproblems are computed before they are referenced. With the dependencies established, our next step is to handle the boundary cases. For instance, as the figure shows, we need to decide how to handle the situations where the dependent subproblems are undefined. First, let's understand what it means to have a left out-of-bound condition. The columns in our matrix represent the candidate items. Specifically, the first column represents the first item, the second column represents the first and second items, and the ith column represents the first I items, and so on. Therefore, a left out-of-bound condition refers to the 0th column and indicates that there exists no item in the current set. If there are no items to choose from, the maximum value should clearly be 0. Now, can we add items to an empty set? The answer is yes. Thus, a left out of bound should not prevent us from referring to the subproblem. We just need to return an appropriate value of 0 to properly handle the special case. Second, let's consider the top out-of-bound condition. Recall that the rows represent capacities. Therefore, a top out-of-bound condition indicates that the remaining capacity is not enough to hold the item. Unlike the previous case, where adding items to an empty set is allowed, adding items without sufficient capacity should not be allowed. Therefore, instead of returning a specific value, we should simply ignore the corresponding condition in the recursive function if a top out-of-bound condition occurs. Based on the above analysis, we can modify the recursive function as follows. If the candidate set I is empty, then the result of VCI will be 0. This corresponds to the left out-of-bound case. If the existing set of items is not empty, we can inherit the items that have been already selected. This is represented by the second condition of the recursive function. The third condition is only considered if C is larger than or equal to WK, meaning that the remaining capacity is sufficient to accommodate the new item K. This aligns with our handling of the top out-of-bound case. We summarize the algorithm as pseudocode here. The for loops in lines 2 and 3 implement the left-to-right, row-by-row table filling order. Line 4 initializes the entry with the smallest possible value, 0, representing the case where no items are selected. Line 5 handles the scenario of not selecting item J by only inheriting the current selection if it is not empty. Lines 6 to 9 consider the case of adding the item J if sufficient capacity is available. Note that the table T used in line 8 is the traceback table, which records whether the item J is selected. Line 12 calls another procedure, traceback, to reconstruct the subset of items to be taken for the optimal solution. This is the pseudocode for the traceback function. Lines 5 to 6 handle the case where the item is taken, and line 8 handles the case where the item is not selected. Note that the majority of the effort of this algorithm is spent on filling up the DP table M, which has a dimension of C times I. Meanwhile, computing each entry of the matrix only requires a constant time. Therefore, the time and space complexity of this algorithm are both OCI. Note that the time complexity is pseudo-polynomial, meaning that it takes a polynomial form but actually grows exponentially with the input size. This is because the capacity C can be represented using only log C bits, which defines the length of the input. As a result, if we let n equals log C be the input length, C becomes 2 to the power of n. Thus, the running time of the algorithm grows exponentially with the input length. Finally, let's run this algorithm on the given instance to see if it finds the optimal solution. For the first entry, it is left out of bound and therefore has no existing selection for it to inherit from. It is also top out of bound, so we cannot select the first item. As a result, it will have a value of 0. The second entry has its left-dependent subproblem well defined, allowing it to inherit the selection from its left entry. Because the left entry has a value of 0, the second entry could take the same value 0 as well. The second entry is top out of bound, meaning that we cannot select item 2. As a result, the second entry will also have a value of 0. Using the same logic, all entries will be 0 until we reach the entry M24. With a capacity of 2, this entry allows the inclusion of item 4. Therefore, the value for this entry becomes 1. For the entry M32, The available capacity of 3 allows for the inclusion of item 2, resulting in a value of 6. For the entry M54, it can refer to the left and inherit from the previous selection with a total value of 9. Alternatively, it can refer to the top left dependent subproblem and select item 4. In this case, the new value becomes the existing value of the top left dependent subproblem, which is 6, plus the value of item 4, which is 1, resulting in a value of 7. Since 7 is less than the inherited value of 9, we will take the maximum value and fill M54 with 9. For the entry M63, it can refer to the top left and include item 3. The resulting total value is 11. Finally, we can perform a traceback to determine the items to select for the optimal solution. The top left arrows shown in the traceback table correspond to the items selected. In our case, they are items 2 and 3. We can verify that selecting these items indeed leads to the maximum value of 11. In summary, we have presented a dynamic programming solution for solving the knapsack problem. The algorithm has both time and space complexity of OCI. Thank you for watching and see you next time.